Hi everyone, welcome to the lecture on 3.1 and 3.2, which is functions and their graphs. In this section, we're going to be looking at relations, which are just a set of ordered pairs that shows a correspondence between two sets. We call set X the domain or the input, and set Y is called the range or the output. You might see this notation here. And we read that as X maps to Y. So that just means if you have, let's say, a group of X's and a group of Y's, and let's say you've got 1, 2, 3 in your domain, and you have 4, 5, and 6 in your range. 1 maps to 4 means you have the ordered pair 1, 4. Okay. So in class I did a candy grab where you measured the length of your hand in inches and then you counted the number of candies you were able to grab. And that was our relation. There was a set of ordered pairs that represented X, and which would be our hand length, and Y, which is the number of candies. So since we don't have that data, let's pretend these are the numbers we got. So if your hand was 6 inches long, you were able to grab 15 candies, and so on. Okay, so one way to represent a relation is a table. As you can see there, you've got a table of X's and Y's. Another way to represent it is just as a set of ordered pairs. So we could call it set R for relation, and we would put this inside our braces. So we have 6, 15 is one of our ordered pairs, 7, 17, and so on. So I'm just going to take each of the X's and Y's in the table and list them as a set of ordered pairs in a set. And that's a relation. So there's my relation. Another way we can represent it is by mapping. So I could take the X's and the Y's and map them as I drew earlier. So you would list the X's, which would be 6, 7, 8, 9, 10, 9.5, and 8.5. And the Y's, 15, 17, 20. You don't have to write any repeats. And then you just draw arrows from each X to its corresponding Y. So 6 goes to 15, 7 goes to 17, and then we have a bunch of the X's go to the same Y value. (9.5 to 21 and 8.5 to 23. So this is a visual way of looking at a relation and determining different features. One of the things we're going to look at is whether relations are functions. And this map would tell me that yes, it is a function, and we'll talk about why that is. So the domain, remember, are just all the X values. And if I wanted to list the domain here, I would list them as a set. So the domain would be all of the X's. And then the range, remember, all the Y values. And the range here would be all of the Y's listed. Another way to represent relations, another visual way, is to graph. So you could graph each of those points. So I'm going to take those points and I'm actually going to graph them on Desmos to save some time, and also so you can see how technology would work here. So I'm going to clear out what's there, and you can list ordered pairs, so I'm going to do that now. So we would do 6 comma 15, you put it in parentheses, and we don't really need them labeled, that's okay. Okay, so as you can see here, that's a visual of all of my ordered pairs in my relation. Okay, so now we want to look at something called a function. And I want to keep this graph here for a second so you can see. So a function from x to y is a relation that associates each element of x to exactly one element of y. So in other words, you can't have the same x values. One way to tell is by looking at this graph, none of the x values are exactly the same. And if they were, the dots would line up vertically, which they don't. So as you can see here. So as you can see in this mapping here, activity level and daily calories, you can see that each x, so if x is activity level, and then y is your dependent variable, right? The daily calories depends on how active you are. Each x corresponds to exactly one y. So right here we have a function. This is a function. All the x values are different. If I was to jump to letter C, C would not be a function because 2 of the x values are the same. So if you were to look at a map of this, you would visually see your x's are -2, 0, 4, and 6, and your y's are 4, 6, 8, and 0. And -2 would map to 4, but then it also maps to 6. So if you ever see more than one arrow coming out of the same x, it is not a function. As opposed to the problem we did here, each x value has exactly one arrow coming out of it. When you get to 8, 9, and 10, they share the same y, but that's okay. You just can't have an x, a y, share the same x. So in letter C, 4 and 6 both share the same x. If I look at B, we've got our relation S, and it equals those ordered pairs. And if I go through and look at all the x's, all of the x's are different. So that's one way to tell that it's a function. Also, as we said, none of the y's share the same x value. Pardon me. Every y has a different x. Another way to tell if you have a graph is whether a relation's a function is to use a test called the vertical line test. So all that says is simply if you draw a vertical line through the graph, if it only goes through in exactly one spot, then that graph's a function, which makes sense because every x would be different. If they were the same, they would be one on top of the other if you were to plot them. So it would not pass the vertical line test. So this is a yes. However, in B, it goes through more than one place. So no, this is not a function because at each of those points that I circled, they would share exactly the same x value. As you can see, like here and here, both of those x values, that would be 6 comma whatever the y value is, and then this would be 6 comma whatever the y value is. So the x's are exactly the same. In letter C, if you graphed y equals x squared minus 3, okay, if you don't know what that looks like, it's x squared, and that is a parabola. So if we type in y equals x squared minus 3, if you were to draw a vertical line anywhere through the parabola, it would go through in at most one place. So that is a function. Another way to represent functions is using symbols. One of the symbols we use is this f with the x in parentheses, and this is read f of x. So it's the value of the function f at the number x. So if we were to take an equation, let's say y equals x squared minus 3. If I replace y with f of x, they're the same exact thing, right? Y is f of x. They're the same thing. This is just saying, what's the y value if I tell you what the x value is? So if I was to plug in -1 for x, I would have in my equation -1 squared minus 3. So -1 squared is 1, and 1 minus 3 gives us -2. So that's telling you when x was -1, y is -2. You could do the same thing with f of 3 equals 6. Plugging into that equation, x squared minus 3, you would replace the x with 3, and you would do 3 squared minus 3. And 9 minus 3 is 6. So when x is 3, y is 6. So let's take a look at the following functions. We have f of x, -2x plus 1, g of x, which is the square root of 3x minus 5, and h of x, another quadratic. We have x squared minus 2x plus 3. So in letter A, if we need to find f of -2, I'm going to take my f function, and I'm just going to replace it with the x with the -2. And all I'm going to do now is I'm going to solve it. So -2 times -2 is 4, plus 1 is 5. So f of -2 is 5, which again just means at -2, y is 5. In letter B, we have 3 times the function g of x. Okay, so that just means I'm going to take g of x and multiply it by 3. So if I take 3 times the square root of 3x minus 5, you can't multiply the 3 to what's inside of the radical or the square root symbol. So you would just leave this as 3 times the square root of 3x minus 5. That's it. And in letter C, this is saying h of x plus 1. So I'm going to take my h function, and everywhere there's an x, I'm going to replace it with an x plus 1. So with this one, you got to be really careful with x plus 1 squared. Remember, that means x plus 1 times x plus 1. So you have to FOIL it. And you're going to do, remember, FOIL is first, outer, inner, last. You're going to multiply the first terms together, x times x, which is x squared. And then you're going to multiply the outer terms, x times 1, which is x. And then the inner terms, 1 times x. And then the last terms, 1 times 1. Now here I'm going to have to distribute the -2. And then add the 3 at the end. Now I just got to combine like terms. So I'm going to put this in descending order. X squared will go first. I'm going to combine my like terms. I have x plus x, which is 2x. But then I have a minus 2x, so they'll just cancel. And then I have a 1 minus 2 plus 3. So that gives me 2. So my final answer is x squared plus 2. One of the other things we want to look at is the domain of a function. It's not always specified. So recall that the domain are all x values. So at times, only the equation of the function is given. And in this instance, the domain is the largest set of real numbers for which the value f of x is a real number. So what I need to do, and I gave you some pointers here, is start out with the domain as the set of real numbers. Okay, and real numbers, remember, are not imaginary numbers. Okay, if the equation has a denominator, you want to exclude any numbers for which the denominator is 0. Because remember, otherwise it would be undefined. Remember, no zeros in the denominator. If the equation has a radical, when I say radical, I mean like a square root, with an even index, so square root, fourth root, sixth root, the number for which the expression inside has to be positive. It can't be negative. So we're going to restrict the values of the domain. So if I was to find the domain of this first function here, we're going to express in set notation and also interval notation, x squared plus 5x. You might be thinking, okay, what does that graph look like? It's just a parabola. And parabolas, they go on forever and ever in both directions. Are there any values that would give you an issue? Any values of x? Well, there's no denominator, so I don't have to worry about restricting any of those values. And then also, there's no square roots. So my domain would just be all real numbers. I can plug in any number I want for x, square it, and add 5 times that number, and I'm always going to get a y value. So here, my domain is all real numbers. In set notation, I would express that as x such that x is an element of the reals, and the real numbers just have a fancy r. In interval notation, remember that would be negative infinity to positive infinity. Okay, for letter B, I have f of x equals the square root of 3x plus 12 over x minus 5. So there's 2 places I need to be careful. First of all, in the numerator, I can't have the square root of any negative numbers because that would give me an imaginary number. So I have to first restrict my domain for the numerator. So I'm going to take the radicand, what's inside, and I'm just going to say, okay, x has to be greater than or equal to 0. Because if it's less than that, I would get a negative, and you can't take the square root of a negative number. So here you're going to solve for x, and x has to be greater than or equal to negative 4. And you can try it. If you plug any number greater than or equal to negative 4 in for x, you can take the square root of it. But if you try plugging in a number that's less than negative 4, it won't work. The other thing we need to watch out for is the denominator. Remember, you can't have 0 in the denominator. So we want to find the value like what number would we plug in for x to give us 0? So I'm going to take my denominator and set it equal to 0, and we would get x equals 5. So 5 is a bad number, because if I plug 5 in to the denominator, 5 minus 5 is 0. Even though it won't give us an issue in the numerator, you can't have 0 in the denominator. So to write my domain in set notation, I would just want to put something like x such that x has to be greater than or equal to negative 4, and then I would put a comma and I would put x does not equal 5. If I was to write that in interval notation, think of a number line, right? So you have negative infinity and positive infinity, and then I've got negative 4 and 5 in here. So you can have any number you want on that number line starting at negative 4 and going towards positive infinity. But there's a problem right here. It can't equal 5. So your domain would go anywhere from -4 to 5, but you can't include 5. So you put parentheses around the 5. And then you use the union symbol, and then it would be anywhere from 5 to infinity. So that's just saying, again, anything from -4, not including 5, is okay, and then anything from 5, not including 5, to infinity is good. The other thing we can do is we can add, subtract, multiply, and divide functions. And here we need to be careful. The domain, if we combine functions, is literally the domains of both functions combined. And remember, when you're dividing, you have to exclude values of x that cause division by 0. So we need to remember that, and that's referring to that last property there for the quotient or dividing two functions. So here I have two functions, f of x and g of x. This first one is saying f minus g of -1. So if you look at your properties, that's referring to the difference property, which really is just saying f of -1 minus g of -1. So if you remember what we did earlier in the lesson, we plugged in -1 for the x values and then simplified. We're going to do the same thing here, except we're subtracting. So first I'm going to take my f function and plug in -1. So I would have -1 squared minus 3 times -1 minus 4. Please remember to put parentheses around what you're substituting. Now I have minus the g function. So I'm going to put g in brackets. I want to group it off. Here it doesn't really matter as much, but in other cases when it's more than one term, you want to make sure you group it because you're subtracting the quantity, not just one of the numbers. So now we have simplified. -1 squared is 1. -3 times -1 is +3. Minus 4 minus -1 plus 2 is 1. And if I simplify in order, 1 plus 3 is 4, 4 minus 4 is 0, and 0 minus 1 is -1. So that, when you subtract those two functions, you get -1 for your answer, okay? Letter B, it says find the values of x for where f of x equals 0. So remember, f of x is just y. So it's saying take y and make it 0. So for the f functions, you're going to have 0 equals x squared minus 3x minus 4. And this is a quadratic. Quadratics we solve different than linear functions. For quadratics, you want one side to equal 0. So it already is. And by the way, if you don't like the 0 there, you can put it over here. It doesn't matter. So you can try a couple things. You could try factoring it first. And if that doesn't work, you can try the quadratic formula. Factoring will work here though. So remember, for factoring, you want two numbers that multiply to give you the last term, which would be -4. And you want those two numbers to add to the middle number, -3. To get my signs, I'm just going to pick the first sign I see, which is a negative, and then multiply the two signs together. Negative times negative is positive. So you want a negative and a positive number that multiply to give you -4, and add to give you a -3. And that would be -4 and 1. -4 times 1 is -4, and -4 plus 1 is -3. So you're going to have x minus 4 times x plus 1 equals 0. And then we're going to apply the zero product property. So here, you would just set each factor equal to 0. So you would get x equals 4 and x equals -1. By the way, those would be the x-intercepts. So that's just saying when x is 4, y is 0, and when x is -1, y is 0. Okay. Next we have function f and g, and now we're being asked in letter A to multiply and state the domain. So when multiplying these two functions together, I'm going to apply this property here, the product property, and it's just saying that this is going to be f of x times g of x. So I'm going to write down f of x, which is 1 over x plus 2, times g of x, which is x over x minus 1. Now, to multiply fractions, just go straight across. You've got 1 times x in the numerator, which is x. And in the denominator, you could multiply x plus 2 times x minus 1. It's not wrong, but you're kind of creating more work for yourself because it's not going to help you simplify anything. And you're going to need it factored in the end to find the domain anyway. So just leave it as x plus 2 in one parentheses and x minus 1 in the other. And then that's your answer. Now to get the domain, remember we start out with all real numbers, but there's a problem. In the denominator, you can't have the denominator be 0. So we need to figure out what values would make that 0. So to do that, we're just going to set both quantities equal to 0. So again, we're applying the 0 product property, and we're going to solve for x. So we already know the answers. Here's x is -2 and x is 1. So they're the two restricted values that the domain cannot be. So your domain, if we were to write it in set builder notation, we would just put x such that x can't equal -2 comma 1. If we're looking at interval notation, think of a number line with -2 and 1 on it. So those are the bad numbers. So x can go from -infinity to -2, but it can't equal -2. It can go from -2 to 1, but it can't equal -2 or 1. And then it can go from 1 to infinity. So that's how you would express your domain in interval notation. For letter B, we're being asked for the quotient, which is divide. So this just simplifies to f of x divided by g of x. So again, f of x is 1 over x plus 2 divided by g of x, which is x over x minus 1. So now that symbol right there just means divided by. And when you divide, you're going to skip, flip, and multiply. So I'm going to skip the top part, which is 1 over x plus 2. And now I'm multiplying. And you're going to flip over the x over x minus 1. And the real word for that is reciprocal. So the reciprocal of x over x minus 1 is just x minus 1 over x. And now remember, you're going to multiply straight across. So 1 times x minus 1 is just x minus 1. And in the denominator, you could just leave it as x times x plus 2. So remember, there's a problem. The denominator can't equal 0. So you're going to take both of the factors, x and x plus 2, and make them equal 0. So this one's already solved for you. This one's not. So the two values x can't be are 0 and -2. They're your restricted values. So your domain, you would just put in set builder notation x such that x can't equal 0 or -2. In interval notation, again, think of a number line, and you've got -2 and 0 on here. So x is okay from -infinity to -2. It's okay from -2 to 0. You just can't use -2 or 0. We symbolize that with the parentheses. And then it's okay from 0 to infinity. So that would be your domain in interval notation. All right, that's the end of 3.2. If you have any questions, please let me know.